Hello everyone, I'm Abeykoon from Queensland University of Technology, Australia. Associate Professor Shaminda Gallage, Josh Murray, and Associate Professor Jessica Trofimovs are the other members of our research team, and our study is on identifying the relationship of landslide initiation and rainfall threshold in Southeast Queensland. When it comes to rainfall thresholds, studies aimed at deriving mathematical equations that represent the thresholds beyond which landslides have occurred in the past, and it is assumed similar conditions for the future as well. A number of rainfall thresholds have been developed in previous studies. However, no compelling attempt was made to establish rainfall thresholds for landslide initiation in Australia, apart from only one study by Ravindran et al. 2019 on northern New South Wales. A significant mean annual precipitation that exceeds 1500 millimeters is usually experienced by the eastern coastal belt of Australia, which is also predominantly composed of mountainous terrains, contributing to a large number of rainfall-induced landslides. Especially in 2011, there were at least 75 building damages, 8 injuries, and 50 fatalities recorded as a result of landslides in the country triggered by significant rainfall leading up to the events. The initial study incorporated the 1,974 landslide events. So as shown in the figure, most landslide events were recorded in Queensland, signifying the importance of examining the potential of landslide initiation in the region specifically. The current study area for the analysis includes southeast region of Queensland state, which is commonly referred as SCQ. SCQ is the most urbanized region in Queensland, which extends for more than 35,000 square kilometers, accommodating over 3.6 million people, which is almost 75% of Queensland state population. Rainfall-induced landslides are common in SCQ. So SCQ experiences approximately 1,050 millimeter annual rainfall, including 450 millimeter reliable summer rainfall. Thus, the most extreme rainfall events that leads to landslides occur during the summer period. Also, notably, SCQ was declared a disaster zone following torrential rains during the summer of 2010-2011. Therefore, the prediction of rainfall-induced landslide is significant for SCQ. Landslide during the period of 1842 to 2018 have been retrieved from the Geoscience Australia landslide dataset, which includes 1,974 landslide events across Australia. The landslide dataset includes 156 landslide events in SCQ. However, certain landslide event records were discarded due to the unavailability of appropriate weather stations nearby and the unavailability of rainfall information. Hence, the number of SCQ landslide events are reduced to 104 events and are depicted as red dot as shown in the figure here. So rainfall data were obtained from the Bureau of Meteorology, Australia for analysis. The BOM rainfall data includes rainfall recordings for every minute, every half hour, and pluviographic information. Initially, the distance between each landslide and each weather station was calculated using the Haversine method as shown in this flow chart. Generally, Haversine method is used to compute the great circle distances between two pairs of coordinates on a sphere, employing corresponding latitude and longitude as input parameters. A MATLAB script was employed to determine the distances between each landslide event and weather station, correlating all the landslide events with the entire set of weather stations in SCQ that generated a database of 23 million calculations. Moreover, a logical function was utilized to examine if the landslide event date falls within the weather station operation period time. If there are weather stations within a 5-kilometer radius from the landslide event, the nearest station was selected for the threshold calculations. Secondly, if no weather stations are available within a 5-kilometer radius, then the closest 3 weather stations were selected within a 10-kilometer radius from the event, and the data from these 3 events were adopted to determine the rainfall correspond to the event based on inverse distance weighting interpolation, where the distances are inversely weighted relative to the prediction location. As mentioned previously, in case of non-existence of appropriate weather stations within a 10-kilometer radius from the landslide event, the record was discarded from rainfall threshold calculations. So based on the collected rainfall and landslide data set, the average rainfall intensity and the duration from the beginning of the rainfall event to the initiation of landslide were defined. Additionally, a rainfall event was defined as the rainfall period delimited by a non-rainfall period of 24 hours or more. In order to determine the rainfall ID thresholds objectively, a quantile regression method was used in the form of I equals A plus B times D to the power negative C, where I is the intensity measured in millimeters per hour and D is the duration in hours. Thresholds were determined for different quantiles, so that includes second, 10th, 50th, and 90th percentile. The second percentile quantile was used to determine the rainfall ID thresholds for SCQ region. The normalized ID threshold was also established by dividing the rainfall intensity by the mean annual precipitation value. For the curve fitting of ID threshold equations, quantile regressions are identified as one of the most best curve fitting options in this regard due to the increased accuracy. Quantile regression provides higher accuracy for cases where the variance may not be uniform within a data set, as the approach considers the median for each quadrant. Hence, the quantile regression varies from linear regression, as methods are based on median and mean respectively. Therefore, quantile regression is well suited for the current study because the historical rainfall and landslide data might contain some errors. The approach employs quantiles which are resistant against outliers and errors. Further, it produces better understanding of relationship between rainfall intensity and the duration values and the occurrence of landslide than compared to other regression models, so providing results with greater confidence interval. The data were analyzed utilizing quantile regression package Contourec in RStudio. The 50th percentile was employed to determine the general trend of rainfall ID conditions associated with the shallow landslides. The rainfall threshold was determined based on the second percentile. The analysis actually produced the threshold equations along with the graphs, so as shown in this figure. So we have given all the equations and the graphs for each SCQ threshold. So developed SCQ threshold is lower than the other global and regional ID thresholds for smaller rainfall durations, especially lower than the threshold of northern New South Wales. The difference is more significant for shorter rainfall duration and decreases with increase in duration. This is primarily due to the larger data set used for the study, which includes both small and large scale rainfall induced landslides. Initially, it was anticipated that the SCQ threshold for the current study would be similar to the northern New South Wales study due to the close proximity of the regions. The study in northern New South Wales needed a higher threshold than compared to the SCQ threshold. The threshold for New South Wales study provides a threshold that corresponds to a 50% chance of landslide occurring, and therefore it is compared with the 50th quantile for SCQ threshold. The comparison of SCQ and Northern New South Wales thresholds demonstrate that the importance of separate models for local regions. Further, the sample size may have been influencing factor for the Northern New South Wales study, considered a small number of events compared to 100 plus events for SCQ. In conclusion, the methods vary considerably for different studies. Therefore, caution need to be taken comparing the results. Factors such as landslide and rainfall data should come into consideration as well. Various sources were utilized to compile the landslide database in Australia and may not be accurate or consistent. The rainfall data had to be carefully reviewed, as many weather stations lacked rainfall measurements for some time period and different rainfall measurement types. Due to the Australia being a sizable flat continent, it proved difficult to find weather stations near many of landslide events, even though there are almost 18,000 weather stations in Australia. Many of landslide events were discarded where the stations were not close enough. Therefore, optimal method for using rainfall data should be explored in the future. So that's it from our study. These are references. Thank you so much.